Okay, so hello, I'm Ondřej, and today I will speak and show you some code about how to create, first of all, extensions in Rust, Python extensions, and then also how to communicate them with Python from Rust using asyncio, which might be the natural way to communicate. So what I'll talk about today is, first of all, I will tell you a few words about Chainkeepers, which is my company, so what we do and where I come from. And then we'll focus on performance of Python and why it might make sense to try to create extensions in something like Rust. And then about why this might be particularly interesting in case of network communication with WebSockets. And then I will show you how this can be done. So Chainkeepers, that's my company. I work there, also Milan over there works there. And we basically said most simply, well, we believe that the decentralized finance really has the potential to change the world for the better and really shape many aspects of our lives. What we do, then we build trading bots mostly at this point in crypto, but we view it more broadly, like trying to understand what things we could do to stabilize DeFi, provide liquidity, then maybe also like provide some other services to the decentralized economy. So we are invested by Mython C, and particularly Ondřej. Probably some of you heard about him. What we mostly use Rust and Python, and we're always looking for like people to talk to who might be interested in what we do, or perhaps then to work together. So definitely reach out if some of this sounds interesting. Okay, so now to the main theme of the talk. So Python's really speeding up, and if it keeps like this, we just need to wait a few more years, and then we'll be at the top performance of C++. But really, Python is maybe 50 to 100 times at times slower than if you write everything in C++ really optimized, which makes sense, but it also kind of sucks if you want to really write fast code and do it in Python. So one of the tools that can help you is Numba. Who knows what Numba is? Or who has used Numba? Like, yeah. So Numba helps you if you have some kind of long computation that you write in Python, and then you can speed it up quite easily and in a straightforward way by using Numba. The other thing that slows Python down is abstraction, which is really nice to have like abstract code and not have everything put in there and wired into your code. But every time you use abstraction in Python, it costs you. Like here's some basic timings. So if you just have a no-op statement, it runs like 5 nanoseconds. Then if you do a call, it takes you 53. But if you do another call, like in the test class, you see that there's def call, and the only thing that it does is he calls like another call. So if you do like one dict lookup on a class and then a call, it's maybe if you would do 2, then it's twice as much time as a single call. So every time you use some kind of abstraction, it costs you time. In a language like C++, this might be optimized away, and you wouldn't even maybe do the other call. So basically, there are then 2 main points where your Python code can be sped up. It's like maybe put away some of the abstraction and not have everything dynamic. It's what Numba does maybe in a loop. But sometimes you want to go through Python and process data in a more structured way more often, and then NumFOCUS cannot really help you because there's still some back and forth communication with Python. Also, there's this thing called GIL. Who knows about GIL, what GIL is? Who could explain? Okay, everybody, so I don't need to go into detail. So basically, like everything in Python is reference counted, and every reference counting has to hold GIL. So GIL is practically held all the time in Python. So if you want to like speed up code, do it in a threaded way, then you cannot really do it by spawning multiple threads in Python. The only thing you can really do is spawn multiple processes, but then it's kind of similar like NumFOCUS. Maybe NumFOCUS, you can use NumFOCUS to process smaller data, but not really small. And you can use, like, if you want to process really big data, it's not a problem because you just spawn multiple processes and then process it in parallel and then combine it all together. Okay, so what can we say about Rust? So Python, to wrap up, is easy, not that fast at times. There are some ways to speed it up, but just if you have a lot of data processing in a chunk. So yeah, I didn't start a timer, but yeah, maybe like 30 minutes from now. Okay, so Rust is kind of a modern C++, I'd say. Yeah, and it can be quite efficient. I'm not that expert in this regard, but even though Rust is quite new, I searched for some benchmarks, and they say that like it might be even faster than C sometimes. Like, so there is not really a performance penalty in Rust that would be apparent, like maybe in Go or something like that. Well, Go is not that fast as C++, but Rust is. So Rust also enforces memory safety, which all the people that love Rust, they really love this thing as well. You might learn to love it too if you do not really protest what Rust is telling you that you need to clone something and do it this way, then do it, and then you'll be fine. So, okay, so and why do I want to talk about WebSockets? And then how are we gonna to arrange the next part of the talk, which is one thing, the Rust extension, and then some measurements about how it actually sped up the code. So in the blockchain analysis world that we do in Chainkeepers, we usually have a lot of data sources and small chunks of data, which is, and if you want to process this in Python, that you are basically always in Python. There is not a lot of computation that you really need to do at once, so that you would you could use NumFOCUS. There is not a lot of, if you maybe would spawn multiple processes, then you would introduce some networking overheads, which is not always what you want, and you definitely maybe don't have a large chunk of data that you would need to process. Maybe in some of the use cases, yes, but if you want to react to something that is happening, this would not be the case. So there might be a little chunks of data and a lot of concurrent sources that you need to read from, and then maybe imagine that you want to eventually combine them into some global decision that you want to act on. And you do not want necessarily to write everything in Rust from scratch, because everything you change, then you maybe have to change the design also at other parts of the program, which might be costly. It might be correct, but maybe it's not what you're striving for at the first prototyping phase. And then, but still speed might be of concern to you, so you don't want to like just use Python. Python is ideal, but you would like to speed it up somehow. So how do I approach this? So how could you speed this up? That was the idea, and then we'll see if it really speeds things up. One of the things that really slows up JSON files or JSON processing, which are really abundant in the blockchain world, is parsing of JSONs. It's kind of fast in Python, but maybe you could do better. And also, the next step of this thing would be to maybe write some custom parsers, which might be even faster. But in Python, this makes no sense because you couldn't really do this. So maybe you want to pass and aggregate data in Rust and then pass it to Python somehow. Okay, so this is RUWS. That's how I call the extension that I'll be showing to you. And so I will talk about the Python part. Then I will talk about the Rust part. And for the Python module, for the Rust module in Python, we use Pyo3. I won't be really like describing it in any detail, but here is a link. If you will then browse through, and the code will be available on GitHub. It is available on our GitHub, Chainkeeper's GitHub. I will say it again at the end of the talk. There's the QR code. You can search for it. Okay, and in Rust, I use Tokio async framework. I'm not sure I can really tell a lot about it. There are multiple frameworks for async in Rust. I don't really know how they differ or how this would apply to this talk. It's just everybody uses Tokio, so yeah. I use it too, like asyncio in Python. There are also like multiple frameworks, but okay. So the Python part. So okay, so for the Python part, what we want to have. So we want to have a, okay, so this is a Python, this is description. I will now describe how the module is laid out, show some code, just to introduce, talk a little bit about the code. I don't know if it will be intelligible. If there are some questions, please ask, and we'll see. And other than that, it will just show how the general layout is, and then you can look it up in GitHub and maybe run the code, play with it a little bit, try to change things. Okay, so the Python part, I will start from the Python part. The Python part wants to just get some stream that is published from Rust. And in Python, you just want to like have some kind of easily usable stream and then run this in an asyncio loop. And then you consume the data and measure the latencies. What the measurement, maybe I will describe also how the measurement is laid out. I have some Python server, like a really simple script that just generates data and sends some kind of data and the timestamp. And then the consumers, then I have a pure Python consumer, pure Rust consumer, and then I have Python with the Rust module. And I just connect to the Python server that really just sends data at intervals and then read the data and compare the time when it was generated at the server and the local time, and then I see how long it takes to get there. So there's obviously the network latency, then there's some jitter because the Python really is not multi-threaded, but then there's some systematic difference between the implementations. Okay, so in Python, what you want to do basically is you have like coroutine main loop, you run it in asyncio. Basically what it does, it just instantiates a stream that's now the stream in Rust. I'll describe later how it is done. And then you just call stream run. It runs the stream, opens the sockets, starts a thread in Rust, which is now Rust is in, it's a module, so you will have two threads in Python, but the one thread, it doesn't really touch jail, so it can run its own way, or its own life, and then Python operates in the second thread, in the main thread, and then when the Rust module wants to communicate with Python, it will like communicate through some async stuff, like through the queue, how I will show later, and only then it needs to obtain jail, communicate with the queue, and then it's then easy peasy doing its job. So, and in the Python consumer, it's like simple async for data in stream, and you consume it. We say like the Rust had put their X time, which is the creation time, and then we obtain our own time, then print it. Then I have like logs, and then I analyze the delays. The task done, it's just, it's not really necessary, but you could really, the queue thing is, as we'll see, stream queue is a async IO queue that was created from Rust, but it's a general async IO queue object, like a Python object, and you can easily call anything on it from Python. Okay, so we have a main. So there was this blank. This is a stream implementation in Rust. We're starting from the back, but from the more familiar things. So I think it's more intelligible. So for the Python to know what stream is, he needs to have a module. So stream will be defined in another module. Here we have PyStream. So PyStream is implemented in Rust. So that's the extension. And for the extension, you need a shared library. And then you need a PyI file. That's this one. And the PyI file really does just say what is there for Python. So there's an init and there's a run. And we have attribute URL queue. Simple. So we have PyStream. So from this PyStream, we will create something in Python. So there is a stream wrapper that enables us to then do the async iteration, which would be here, right? This thing. So I have a PyStream that's from Rust. PyStream is a Rust module. Now I have stream, and it is a wrapper. He has stream and queue, and then this thing, this getter, really creates just a proxy. So everything I can call, everything I call on stream that I don't have defined is forwarded to the Rust part. And then I have the iterator here, so I can do the main workhorse is async IO queue. So I will wait on the queue until there is something there, and then I will yield it in the async iterator. If there is an exception, I will raise an exception. So Rust does not really raise exceptions on its own. He just passes it through the stream, and if Python sees an exception, it raises. This is quite arbitrary. So now we have a Pythonic field for a class. So we have a WebSocket stream implemented in Rust that can be really easily consumed in Python. So what do you need to provide on the Rust side? So Rust will do an async, like now it is async Rust, async WebSocket connection, and then if it has some data, we'll send it to Python through the queue. And yeah, then you need Python bindings, and also you need the shared library. Okay, so let's start from the end again, from the simple things. So first, the whole Rust build system is built around cargo, and this is here just to show that really all that you need to create a Python shared library is you need for it to have a name, and then you put there CDI lib, and then it creates a shared library. And this is basically all. Then you have some dependencies later on, but this is the build for Rust. Okay, and then you need librs, which would be like the implementation of the library. And again, in the code on GitHub, this is like at the end of the whole module, but it's again the simplest things first. So here it's Python. His Rust function that does the initialization of the module. So as I was saying, we're using PyO3. It's a framework in Rust to write Python modules, and it provides all those kinds of nice macros. So who here has seen Rust or used Rust? Okay, so 5 people. So let me describe this a bit. So in Rust, hash something is a macro. The macro basically can act on this is the decorator or a macro, and it can then act on the code and rewrite it somehow or write some other code. So the Py module is from PyO3, and PyO3 we named this lib ruws. And PyO3 manages to he sees this as some kind of initialization code, and on loading, the Python interpreter will load the library, and then he needs to run some initialization code to make the symbols and classes and everything available to the Python runtime. So this is how we create it automatically. And the only thing we need to initialize some kind of logging. And then if we have a class, which we'll see that is defined later, we just use really simple, like M is this Py module that we obtain from the framework, and we just add class, simple. And if we want to add exception, we need to define exceptions beforehand. You can look it up in the code. It's also like one-liner simple macro call. You just define exception, and here you edit stream ended exception. It's like stream ended. This would be the Rust part, and then you register it for Python. So also some Rust things, or one thing in Py3 there's this Python thing, like Python, that's everywhere, and it's written here. Like that's just represents the GIL log. So all the interactions in Py3 with Python, they usually need this Python object that represents that you obtained the GIL. We'll see how you can obtain it, but here the framework obtained it for us, and it just passes to us, and so we just can add to the module, then get the type, and everything's okay. So some Rust specifics also. In Rust, you don't have exceptions. So every function can signal errors, but it signals errors by values. So if a function can fail, it always returns result. So this is Py result. There are multiple variants of results, which gets quite kind of annoying, at least for me. But yeah, you can then convert, and but if you don't know how to convert, then it fails. But here is no problem, because the framework really understands Py result, and if something fails, he sends an error, and if everything passes, here we have OK. Notice that this line does not have a semicolon. All the other lines have it. So if you add a semicolon, it's a statement. If you don't, this is a return value. So the only thing that does not have it is the return value. If you would add it here, he would complain that there's no return value because you would consume it. And also a Rust thing, there's this question mark. Question mark is a magic thing in Rust, because basically everything can, as there are no exceptions, a lot of the functions signal errors by being either OK or being error. But if at every line you would have like match, call, OK, error, then you would be like really unreadable. So if you don't really care or don't want to handle the error, you just add a question mark. And if it's an error, if it results in an error, the whole function will end in an error. And if it's OK, then it just falls through to the next line. So yeah. OK, so that was a bit of Rust. And also this is really simple. So registering the module, really simple from the Rust. If you have the objects in Rust, simple. Any questions, maybe? Or, OK.
So maybe
Yeah.
I have a question.
Yeah.
So how the stack trace looks like if anything fails on one of these lines?
Oh.
How can I debug when it happens?
Well,
Right.
OK. In Rust, basically the type checker usually like tells you that it does not compile. So if it can fail somewhere, the one thing is that it does not compile. And if there is an error that falls through, I guess you would get it during loading. But I haven't seen it. So, but you can try it, and you can take the code and then maybe replace this with error and see what fails. But I would expect that Python would fail somehow upon loading. Or maybe he converts the errors into exceptions somehow transparently. I'm not sure about this. Okay. So this was the registering. So the next thing. Now I have a main RS, but this is actually not main from the module. This is a main from the Rust implementation, and it's here to show how you would do the loop in Rust, like the consumer part, where it connects to a WebSocket and then does something with it, and then maybe ends. So. Initializes logging, then you have like macro calls end with a bang. So if there is, in Rust, again, if there is a bang at the end of identifier, it is a macro. So a macro, there's some kind of rewriting language. He sees all the tokens that you pass in. It's not really Rust, but it's just some kind of macro language manipulating with tokens, and then there is some result, and then it tries to compile it. I'm not really sure why it's needed here, but basically mostly because of the conversions of the types. They don't really happen automatically in Rust, so you would use some kind of macro. Okay, so this thing then spawns a coroutine in the Tokio framework. This would be like async IO loop, how is it called? Start tasks? Oh. Like in Python, you would just start task, like not awaiting it, but starting it like concurrently. That's what this does. And so he starts this. The move is needed because of Rust move semantics. I won't go into detail at this line. So this starts a coroutine connect, which really connects to the WebSocket and waits for data and then prints it. And this one sleeps, and here is a wait. So this might be similar to if you would do in Python, like spawning a task and then waiting forever until you're done. Okay, so this is like the Rust part. Okay, so how could connect look? How would connect look? Okay, so we have a URL. What's interesting here? Like we use tungstenite to connect, and then there's one interesting Rust thing. You see that all the error handling is quite verbose. In Python, maybe we just hope that it will succeed or throw an exception and be okay with it. Here you need to react, or because otherwise you cannot really get the data from the send. You might be okay by putting there the question mark, but otherwise not. If you have the next part, so now you connect it, and you would use connection next. It's similar to Python. Await really does the similar things, and then you get data. You need to parse JSON data. Here I have a note, like there's a parser, and if you would parse JSONs in Rust, maybe you'd use the JSON, some kind of general structural data parser. It was it was really slow. If I fed it a lot of data, it was really slow. So JSON parse didn't have that problem. So maybe if you want to have don't care so much about the structure, but care about the speed, maybe this is better. Okay, so now here we have data. Now, where did we obtain it? Here, like there's data. So if I had I had some item, this could also be like in Python, or how could I ask? Like in Rust, you can have this let does implicit pattern matching. So from this await, you can either get some or none. If there is no data. If you get none, you get failure. But here it's like always data. So, and the data is item. Then if it's text, you parse it here. If it's okay, so the item can again be some kind of error. So if it's an error, you don't do this. If it's a text, you parse it. And if it's anything else, you assume it's an error. You just print it and terminate the connection. So now we have in data, we have our data that we want to process further. So okay, so and here comes the interesting Python connection part. So I have my data, and I parse data time, which is like a really arbitrary data format. That's the time that the server created the data. I want to compare that time to the local time. So I have this time, get timestamp, and now I need to interact with Python. So I need to obtain GIL. I can do this by Python with GIL. And then he calls this closure. He obtains GIL and calls this closure with Py. And to create a dict, this might be elaborate, but this feels kind of nice. So I just pass a list of tuples and then call into PyDict. And what he really does, he creates some kind of Python object and also sets it up to be reference counted in Python, and then like increases the reference count. The nice thing is that working with reference counted data might be at times way simpler than caring about the Rust copy move semantics, because if it's reference counted, it's something it is kind of a smart pointer in C++. So basically every time you pass it, you can freely copy it, clone it in Rust, and he just increases the reference count. The only bad thing about this is if you want to interact with the reference count, you need to GIL. So you cannot really use some kind of clone in Rust. You just need to call again to ref or to object and pass it with the Py. You will see this maybe in the code on GitHub. So if you have the dict, then we have some kind of queue, which we'll look more into. That's some kind of wrapper around the Python queue to be usable in Rust and be passable around and not violate the memory constraints. And then we have some method pushPy. It's also a method I will show how it is implemented, and just push the data. He needs the method to interact with the queue. We also need GIL, and we already have GIL here, so we just pass it along. So that's how the interface is designed, and push the data. Okay, so now more in how the queue could be implemented. So that's this thing. The queue in the code before here. This queue is this kind of object. So it's PyAsync queue struct in Rust, and we have a few methods implemented. This is a new method. So this method instantiates the PyAsync queue. What it does at the end, so how the it a string, so you need construct new string, new Python string in Rust, again jail, and then put no wait. So this is really a call that would, in Python, you would just say get utter q, put no wait. And here you can write it like this. Call soon thread save, that there was something similar but way longer, so I just didn't put it in the slide. And then I save q. To build q, I need to call Python, so that's here above. So again, I need jail, I obtain it like before. And then I really like this for some reason. Like you just call Python. It's not a big deal. So you need to import the async IOQ and then just eval q, and you get q. Then you need to run into Py, which really from the Rust kind of object, you will get a new reference, increase reference count so that you can keep it. That's this thing, and then you can put it in here. Otherwise, you wouldn't be able to do that. And get running loop, something really similar like this thing. It just calls async IO get running loop, and so that we can query call soon thread save, which is what we'll need later on, and save it. So this is how we construct PyAsync q. And then what we also needed was q, and we need push Py. So how is push Py defined? So push Py. It's a method on the queue, so Rust gives us self, which we can then use. It's a reference to self. Then also we defined it so that we already have jail, so that we don't have to re-obtain it again. So we have this Py thing, and then we have some kind of value, and the value can be converted to Py object. This is like set with this, and then so in Python, what do we want to do? We want to do call soon thread save, and then q push no wait data. If it was Python, and if since it's Rust, we need to convert the value to Python object, but we already have the references to put no wait. We already obtained it before, and we have a reference to call soon thread save also. So, and call one is just a PyO3, so the framework's way of saying like we need to call it. So to wrap it up, basically what I just described is you can have general any kind of processing in Rust, and then if you want to communicate back to Python, you just really use a queue and push it there in kind of Python way. So now then I was interested in whether this actually helps with anything, or whether there is, well, there might be a few things going wrong, right? Or go wrong. Like either the parsing part on the Python side might not be that bad, and the overhead not that large, so that you wouldn't really notice how much Rust speeds things up. Or it could happen that if you would have pure Rust implementation, that would be really fast. But if you would just write a module that would communicate with Python anyway, then a lot of the overhead would come from the communication to Rust, from Rust to Python back. So you would anyway not get any improvement, and you would need to just implement everything in Rust and discard Python altogether if you would need speed. So how was the benchmark done? I already described this a bit at the beginning. So there was a Python server feeding some data, some JSON data points at 10 milliseconds each. And then there was a pure Python code which used or JSON, which is kind of a fastest JSON parser I know of. Then there was a pure Rust implementation that used this JSON Rust parser, and then there was this Rust module, but the final consumer was Python, who would timestamp and print the latency information. The module also used Rust JSON, and then I measured differences between the times, like the server created the data, timestamped it, and the client read the data, parsed it, timestamped it, and then printed out the results. Also, the printing could have affected the delay, and I would imagine that this might also be this would penalize all Python, all the Python clients, right? Because in Rust you would be really able to print fast, but in Python no, and it would not depend whether you use Rust to get the data or not, because the print would be slow. So, okay, so results. So for the data, I have timestamp, and then I had 300,000 of A's in an array, JSON, like a long data array, whatever. And I let it run for 10 minutes, and then I compared the logs. So here, what you can see, this is the pure Python implementation, this is pure Rust, and this is the Rust module in Python. You can see that basically the Rust and Python module, the Rust and Rust module are pretty close, which was kind of surprising, because I expected there would be more penalty here. And okay, so Python's 6 times slower. I expected like to be more slow, but possibly it's like there was this network also effect, and it's really, I think that it has sense just to compare the variance and not really draw any general conclusions about this. So, but the penalty, like the time of communication from Rust to Python seemed not to be really bad. Like maybe like really on a scale of a function call, which like also seems too little, but it's what the data says. I also tried with smaller data, which would be more realistic to our use case, because we don't really have such big data blobs. It's really possibly like a blockchain transaction would be maybe like 100 characters, maybe 100 to 300 characters in total, JSON. So I tried with 5 A's in an array. So really it was just a timestamp, not really longer, and then maybe 5 A's. And here the Python and the Rust module really seem close. So, but here the difference is not that bad. Like before with the big data, Python was really slow. Like if you were only using Python and then you would use the module, you would get a really big speed up. Here, not so much. But anyway, the approach works, it seems. So, so there were 2 aims in this. Like first, explore how you could do this. There might be also other use cases to write Rust modules. For the blockchain application, there are some protocols that only have bindings to Rust, so you don't really, you want to use Rust just for the sake of having some kind of integration possible. But also for speed up, this can be used. So the Python Rust overhead is not that big, expected more. And okay, so it seems you don't really need to give up prototyping, and you can just rewrite parts of your code in Rust and then gain speed. And remember that simpler is usually faster.